Okay, section 2 is going to be on the intensity of sound, looking at the decibels and different ways of measuring how loud sound is. So here is your what do you think questions. The members of rock bands generally protect their ears from the loud sounds to prevent damage to their hearing. So how do we determine the loudness of sound? What quantity is sound measuring and what units are used? Think about that. Now, name 3 ways you can reduce the loudness of the music heard by a person in the audience. Okay, you should have three ways. Okay, so vibrating objects do work on the air as they push against molecules. The molecules that are next to the object, so think of a tuning fork, the air molecules next to it, the tuning fork is doing work on those molecules. The intensity is the rate of energy flow through an area. So what is the rate of energy called? We've learned this one before in previous chapters. It is power. Remember the change in the work per time, or work is also, according to the work energy theorem, work is equal to the change in energy. So the rate of energy flow, the change in energy per time, is then called power. Since those waves spread out spherically, you have to calculate the area of a sphere. What's the equation for a sphere? The area of a sphere. It is 4 pi r squared. So how do we put these two together? How do we find the equation for intensity? Because we have to look at the spherical. So intensity is equal to the power over the area. Power per area, and the area, remember, is 4 pi r squared. R is the distance from the source, wherever the source of the sound is. The SI unit is a watts. W is watts as a unit, not work. Watts per meter squared. This is an inverse square relationship, so by doubling R, if you double R, it reduces the intensity by 4, because if it's 2R now, 2 squared is 4, you're dividing by 4. So that's why it's called an inverse square relationship. If R is halved, you have half R, half squared is 4, so you're going to increase the factor by 4. The intensity scale is based on human perception of loudness. The base unit of the scale is the bell. So more commonly we use decibel. So decibel, the deci part is that metric prefix, deci. So D, big B, is used. So 0.1 bell is equal to 1 decibel, and etc. The lowest intensity humans can hear is assigned a value of 0. And we're looking at loudness, so the same pitch because we're not changing pitches, we're just looking at loudness. The scale is logarithmic, so each increase of 1 bell is 10 times louder. So an increased intensity of 3 bells is 1,000 times louder, and so forth. So here is a table that will tell you the intensity. That's the intensity units, the SI units, but we're going to use bells or decibels. So this is the threshold of hearing, where you can start to hear things at that loudness level. Rustling leaves have about a decibel level of 10. A quiet whisper is 20. A normal whisper is about 30 decibels. The mosquito buzzing in your ear is about 40 decibels. Normal conversation, when you're having a conversation with your friends, probably not in the lunchroom because you're probably a little louder, but a normal conversation is 50. An air conditioning unit at 6 meters away, about 60 decibels. A vacuum cleaner is about at 70 decibels. Busy traffic or an alarm clock is usually at 80. A lawnmower is about 90 decibels. We probably don't have much access to a subway, but a power motor is about 100 decibels. An auto horn at 1 meter is 110. Okay, a threshold of pain. So this is where you can actually feel a little bit of pain in your ears because something is so loud. That's at 120 decibels. A thunder clap, one of those really sharp thunder, not rumbling thunder, but one of those sharp ones from a sharp strike of lightning, or machine gun, 130. Probably don't have much access to machine guns. And then if you are near an airport and you hear that jet plane take off, it's 150 decibels. So let's look at these problems. The intensity of sound from an explosion is 0.1 watts per meter squared at a distance of 1 times 10 to the third meters. Find the intensity of the sound at a distance of 5 meters, 500 meters, 100 meters, and 10 meters. Let's just pick one. So we can find, well, what's our equation first? So if we remember, the equation is intensity was equal to power per, and it was the area, which was 4 pi r squared. So we can do it either, we can actually calculate it, we'll find P would be about the same, or think about, okay, if this is, let's just put 4 pi, and this is 1,000 squared, and now I'm reducing it down to this next one, 500. So we're taking half of it. So remember, if we said that if the radius was half, we're going to have 1/2 r, but this is all squared, so that'd be 1/4, but it's in the denominator, so intensity would, would increase by 4, a rate of 4. So you just, so our intensity would equal 0.4 watts per meter squared. Let's check that. Yep, 0.41, okay. So we, and then the next one from the original, we're dividing by 10. Okay, so you'd actually, we're dividing by, if we're reducing it by 1/10, 10 squared is 100th, 1/10 squared is 100th, so we're multiplying by 100. So when you multiply by 100, that's going to move it over and you get 10. So that's how I would go about doing it. I wouldn't actually plug it into an equation. You're just going to look at the equation. Remember, it's an inverse squared relationship, and so you're going to be able to figure out how that original intensity is going to change based on the change in distance. Okay, so we're just going to look back at table 2, and if our intensity, let's look at that first one, 0.1 watts per meter squared. So 0.1 is right here, so that's about 110 decibels. Oops, the wrong way. There we go. So the first one was about 110 decibels. So that's all they did here, is just correlate the different intensity levels that you solve for to decibel levels. So we kind of talked about this, that the threshold of hearing is the softest. We looked at the 0 decibel, and then the loudest sound that you can tolerate is called the threshold of pain. That is at about 120 decibels. And it does depend on frequency and the intensity. At the very bottom, well, there is a tone generator that you can test your hearing based on frequency, but the human hearing does rely on both the intensity and frequency. So this is showing a graph of intensity versus frequency. So you're looking at pitch here with frequency. Intensity would be loudness. So the area of sound, the threshold of hearing is this line. So at this high frequency, you can have a little higher intensities that you can hear. If very low frequencies, you have to have a higher intensity or you'll be able to start hearing it. You can start hearing it a little quieter when you have a higher frequency. So you can see here's the speech region and the music region, and then here, this line at the top here is the threshold of pain. Let's look at this video looking at how sound in the ear, and we'll talk about human hearing.
Sound wave vibrations in the air pass through the auditory canal and cause the tympanic membrane, or eardrum, to vibrate. These vibrations are transmitted through the small bones of the middle ear to the oval window, a thin membrane which separates the middle ear from the inner ear. The inner ear contains the cochlea, a special sensory organ that converts the vibrations into nerve impulses. The cochlea is a long, coiled tube consisting of 3 fluid-filled chambers. The organ of Corti is found in the middle chamber. The membrane below it contains reed-like fibers. Differences in the physical characteristics of these fibers allow them to vibrate in response to different frequencies of sound. As a vibration pushes on the oval window, the fluid inside the cochlea is set in motion. The wave travels through the cochlea until it vibrates a fiber whose natural frequency matches its own. This motion causes the bending of very small hairs and the excitation of the nerve fibers at their base. Because only certain fibers vibrate, only certain nerve cells are excited. The nerve impulses travel along the auditory nerve until they reach the auditory centers in the brain, where they are interpreted as sound.
Isn't hearing just amazing? I mean, only certain fibers vibrate based on which frequency it is in loudness. And that is how we determine speech, any sound. Okay, sympathetic vibrations occur when a vibrating object forces another vibrate to vibrate as well. It's like a piano string. It vibrates the sound, it hits the string, it vibrates the soundboard, and then that makes it a little louder. The guitar string vibrates the bridge, but then inside the vibrations will reverberate. This makes the sound louder and the vibrations die out faster, and the energy is transferred from the string to the soundboard or bridge. Okay, resonance. They did talk about natural resonance in that little video, but it is, let's say we have 4 bands, our rubber band is linking those 4 pendulums. If the blue pendulum is set in motion, right here, only the other blue pendulum will have the large amplitude vibration because the pendulum is the same length. The others will just have a small amount. So that's what's called resonance. Since the vibrating frequencies match, the blue pendulum are resonant. Large amplitude vibrations produced when the frequency of the applied force matches the natural frequency of the receiver. And so that's why only certain, if you think of those fibers in your ear, like the pendulums, only certain fibers will vibrate with large frequencies, like large vibrations, that they're resonant with that sound, and so only certain ones will vibrate and send that signal. Bridges have collapsed as a result of structural resonance. The Tacoma Narrows wind in the wind is a perfect example of how even in nature things have natural resonance. If you look at a stop sign in the wind, it will vibrate or kind of turn at a certain frequency, and that's its natural resonance with that with wind. During an earthquake, there are waves being produced in the land, in the solid land that the bridge is attached to, and so it will collapse. Okay, this is talking about resonance.
Vibration of one object can cause another object nearby to vibrate as well. If the second object can vibrate at the same natural frequency as the first, large vibrations will occur in the second object. This phenomenon is an example of resonance. Resonance occurring between a vibrating tuning fork and a guitar string is greatest when the frequency of the sound wave produced by the tuning fork is the same as the fundamental frequency, or lowest frequency, of the guitar string.
Okay, so now think back to these questions. How do we determine the loudness of a sound? We take the power per the area. And what quantity is loudness measuring? It's measuring the intensity. And what were those units? It was watts per meter squared. And 3 ways you can reduce the loudness of the music heard by a person in the audience. Well, one, they talk about up here, you could use some sort of ear protection, earplugs, something like that. You could get farther away from the speakers. Is another common one. And then something else, you could turn down the volume on the speakers itself. Not that a person in the audience would have control over that, but that would be a way of reducing the loudness.